bolting a nut may look simple, but the engineering behind them is incredibly precise. In this video, we are designing a complete M16 by 2 isometric thread assembly in SolidWorks, from standard dimension and realistic threads all the way to a fully animated final assembly. Let's build it. Before we start modeling, let's take a look at the engineering standards we'll be using for this project. First, I'll open the ISO 4014 table for the bolt, and here is ISO 4032 standard table for the hex nut. Now let's jump into SolidWorks and begin sketch on the front plane. I'm going to jump back to a bolt dimension table. It's ISO 4014 standard table. This table contains a standardized dimension and thread data for metric hex bolt from M1.6 all the way up to M64. But for this project, we are focusing on the M16 bolt, right there. At the moment, the most important dimension for us is the values labeled S and K in the technical drawing. The S dimension defines the width across the flats of the hex head, and the K dimension defines the head thickness. For M16 bolt, the S dimension is 24 millimeters, and for the K dimension, the ISO standard actually provides both a minimum and a maximum value. The minimum value is 9.7 millimeters, and the maximum is 10.3. And because of that, I'm going to take the midpoint value of 10 millimeters. This keeps the geometry clean while still staying with the ISO standard tolerance range. I'll begin by sketching a 6-sided polygon and adding a vertical relation. Using the dimension we just found in the table, I'll set the width to 24 millimeters. Once the sketch is fully defined, I'll create an extrude boss with a blind depth of 10 millimeters, which corresponds to our K dimension. And there we have the basic bolt head geometry. Let's return to the dimension table. For the bolt shaft and thread, we are interested in 3 parameters, B, D, and L. The D dimension represents the normal bolt diameter. Since we are creating an M16 bolt, the D value is 16 millimeters. The L dimension represents the overall bolt length. And according to this table, if the bolt length L is 125 mm or less, the thread length B is 38 mm. For bolt length greater than 125 mm and up to 200 mm, the threaded length increases to a 44 mm. I'll start a new sketch on the front face of the bolt head. I'll create a circle with a diameter of 16 mm. This represents the nominal diameter of our M16 bolt. Next, I'll use an extruded boss feature to create the shaft. For extrusion length, I'll enter 125 mm, which is the bolt length we selected from the ISO standard table. Before creating the thread, I'm going to add a few finishing details to the bolt. I'll start with the 2 mm chamfer at the end of the shaft. This feature helps guide the bolt into the nut and improves thread engagement during assembly. Next, I'll add a small 0.2 mm chamfer near the bolt head. It's a very small feature, but removes the sharp edge and gives the model a cleaner and more realistic appearance. Now let's refine the bolt head. On the top face, I'll create a sketch and draw a circle that's tangent to the 6 sides of the hexagon. Using this profile, I'll create an extruded cut, which is going to be roll, flip the cut direction, and apply a 30-degree draft angle. This produces the characteristic shape commonly found on standard hex bolt and gives the head a more finished look. With the bolt geometry complete, we're ready to move on the thread creation process. Now it's time to create the external thread. I'll start by selecting the thread feature in SolidWorks. Next, I'll select the circular edge located between the shaft and the 2 mm chamfer. For the thread start position, I'll apply an offset of 3 mm. The next step is selecting the thread standard. For this model, I'll use a metric die thread. Before choosing the thread size, let's return to the ISO table and verify the thread pitch. The pitch value is listed in the P column. If we move across to the M16 row, we can see that the pitch is 2 mm. This means the thread advances 2 mm with every completed revolution. In the size list, I'll select M16 by 2, which match the dimensions specified by the standard. The final parameter we need is the thread length. According to the table, the length is 38 mm. I'll enter a thread length of 38 mm. After confirming the feature, the external thread is completed. But there's one final detail I'd like to improve. To create a more realistic thread, I'll select the face where the thread ends and start a new sketch. Then I'll use the convert entities command to capture the existing edges. With the profile created, I'll perform extruded cut through all. This removes the excess geometry and creates a much cleaner thread termination. Now I'll assign an IC 1020 cold rolled steel material to the model. This is a commonly used low carbon steel that offers good machining ability and is often used for general engineering applications. Next, I'll enable a real view graphic to improve the visual appearance of the model. I'll save the document and then we'll move on creating the matching hex nut that will complete the assembly. Now let's create the matching hex nut. I'll start by creating a new part document and opening a sketch on the front plane. Before modeling the geometry, let's take a look at the standard dimension. For the nut, we'll use the ISO 4032 standard for hexagon nuts. I'll zoom in on the M16 row, since that's the size we are matching for our bolt. At the moment, we are interested in two K dimensions, and that is S and M. The S dimension defines the width across the flats of the hex nut. Just like our bolt, the value of S is 24 mm. The M dimension defines the thickness of the nut. According to ISO standards, the value ranges from 14.1 to 14.8 millimeters. For this model, I'll use the midpoint value of 14.5 millimeters. Just like before, I'll use a six-sided polygon to create the hexagonal profile. To ensure the nut is properly oriented, I'll make one of the polygon sides vertical by applying a vertical relation. With the sketch fully defined, I'll create extrude both feature. Using the midpoint option, keep the geometry symmetric, and with that the basic shape is complete. Next, I'll create the chamfered opening of the nut. I'll sketch a circle on one face and make it tangent to the six inner edges of the hex profile. Using this sketch, I'll create extrude cut through all and apply a 30-degree draft angle. The nut gain the characteristic shape found on standard hex nuts. To keep the geometry symmetric, I'll mirror the chamfer feature across the front plane. This creates the same shape on the opposite side and completes the outer profile of the nut. Next, let's return to the standard table for one more important dimension. Before an internal thread can be created, a hole must first be drilled. The thread is then cut into that pre-drilled hole. According to the table, the recommended drill size for an M16 thread is 14 mm. Now I'll create the hole that will receive the internal thread. On the front face of the nut, I'll start a new sketch and draw a 14 mm circle. Then I'll remove the material using an extruded cut through all. Next, let's take another look at the engineering drawing. Here we can see that the drill hole has a chamfer of 120 degrees on both sides. These chamfers helps guide the bolt into the thread and create a cleaner transition at the entry and the exit points. Back in SolidWorks, I create 0.75 mm chamfer with an angle of 120 degree on both ends of the hole. With that complete, the nut is ready for the threading operation. Returning to the table one last time, we can see that the thread pitch for M16 thread is 2 mm. Now I'll create the internal thread by selecting the edge between the chamfer and the hole. I'll apply a 3 mm offset and reverse the direction to position the thread correctly. For the thread length, I'll use a blind depth of 18 millimeters. Next, I'm going to choose an M16 by 2 thread and I'm going to select metric top. That's matching the bolt with that we created earlier. After confirming the feature, the internal thread is complete and the nut is ready for assembly. With the nut complete, I'll assign the same cold rolled steel material and save the part. Now it's time to bring both components together. I'll start a new assembly and insert the bolt first, followed by the nut. To align the components, I'll create a concentric mate between the nut and the bolt shaft. This places both parts on the same center axis and prepares them for assembly. Before creating the final motion, I'd like to verify that the threads are aligned correctly. To do that, I'll open a section view through the center of the bolt. This allows us to clearly see both thread profiles and check how they interact. I'll slightly reposition the nut until the threads line up correctly. The next step is creating a realistic thread motion. For that, I'll enable temporary axis. Inside the mechanical mate options, I'll choose screw mate. To create the screw relations, I'll select the outer cylinder face of the nut and the temporary axis of the bolt. Those two references allow SolidWorks to connect rotational and linear motion. For the revolution distance, I'll enter 2 millimeters. This value comes directly from the thread pitch of our M16 by 2 thread. That means every full revolution moves the nut exactly 2 millimeters along the bolt. After confirming the mate, I'll test the assembly by rotating the nut. As expected, the nut follows the thread path and advances along the bolt just like a real fastener. This confirms that the dimension, thread geometry, and assembly constraints are working together correctly. Once everything looks good, the section view is no longer needed. Before creating the animation, I'll add a limit distance mate to control how far the nut can travel. I'll select those two faces and using an advanced mate, I'll choose limited distance. For the maximum value, I'll enter 125 millimeters, which corresponds to the overall bolt length. For the minimum value, I'll enter 86 millimeters. This prevents the nut from moving beyond the threaded section during the animation. Before creating the animation, I'll rotate the nut and verify that it can travel correctly between the minimum and maximum limits we defined earlier. Everything looks good, so I'll move the nut to its fully tightened position. Now it's time to create the animation. I'll open Motion Study at the bottom of the screen, but if Motion Study isn't visible, you can quickly find it using the search command tool in the upper right corner of SolidWorks. After expanding the motion study timeline, I'll drag the end marker to 20 seconds to define the animation length. Next, I'll add a rotary motor and select the front face of the nut. For the motor speed, I'll enter 50 RPM. It's important to make sure that rotation arrow point in the correct direction. Otherwise, the nut will rotate the wrong way. After confirming the motor settings, I'll calculate the motion study. The nut rotates, follows the thread pitch, and travels along the bolt exactly as expected. Let's take a closer look at the animation. And finally, view the complete assembly in motion. And that is how you can create a fully threaded M16 bolt and matching hex nut using ISO standard dimension in SolidWorks. Thanks for watching, and I'll see you in the next tutorial.